Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with a tutorial on graphing general rational functions. Prior to watching this, you probably should have watched my earlier tutorial on graphing simple rational functions. This will go beyond that and handle more complex functions. And our procedure today, we're going to be using a combination of algebraic methods and a graphing utility to get a complete picture of the function. Algebraic methods we'll be using to find the domain, the vertical asymptotes and holes of a function, horizontal asymptotes, and the x and the y intercepts. We'll then fill in the remaining part of the function using a graphing utility. If we didn't have a graphing utility, we would have to generate a table of values to fill in the values of the function in between these key points that we're going to be finding up here. Now you might wonder, why don't we just use the graphing calculator to get our graph? And we'll see when we get to the example, there are certain details about the function that we would miss if we were only using the graphing calculator. Things like holes are not easily found on the graphing calculator. The exact values of where the asymptotes might be are not also easily seen on the graphing utility in all cases. So let's first talk about these algebraic methods and how do we find these key attributes of a function. So I'm going to go through each of them one at a time. So if you remember, domain is a list of all the values of x for which a function is defined. Now, for most times when we're looking at domain, instead of generating a list of all the ones that are defined, we look for excluded values. And for rational functions, the values that we have to exclude will make the original function undefined, and it'll do that by making the denominator of the rational function equal to 0. So if we find any values of x that make the denominator 0, we'll be excluding them from the domain. Now the function is undefined at those values of x. And at those places, we can have two kinds of features. We can have vertical asymptotes, which are vertical lines that the function doesn't cross, or we can have things called holes, places where the graph will appear to be continuous, but at a particular value of x, it will skip over that value of x. To distinguish between those, we will be factoring our numerators and denominators to find values that make them 0. Holes occur at places where both the numerator and the denominator equals 0. If we substituted in that value of x into the function, we would get 0 divided by 0, which is a undefined value, but it's a special kind of undefined value. When you get into calculus, we'll be talking about those as being indeterminate. Vertical asymptotes happen at places where that value of x only makes the denominator equal to 0. So if we were plugging in the value into the original function, we would get some finite number other than 0 on the top, and we would get 0 on the bottom. And in those cases, we'll have these features called vertical asymptotes. Now we've talked about asymptotes, both horizontal and vertical asymptotes, in our earlier tutorial. Okay, to find the horizontal asymptote, now there will only be one of those if it exists, and what we have to look at when we have a rational function, we're going to have a polynomial in the numerator and a polynomial in the denominator. And what we're going to be looking at is the degree. Remember, the degree is the largest exponent of a polynomial. So we'll be looking at the degree of the numerator versus the degree of the denominator. And we've got three different situations here. If the degree of the numerator is smaller than the degree of the denominator, our horizontal asymptote will be y equals 0. If the degree of the numerator and the denominator are the same, then we find the horizontal line is going to be the value of the leading coefficient in the numerator divided by the leading coefficient in the denominator. And if the degree of the numerator is bigger than the degree of the denominator, then we won't have a horizontal asymptote. We'll see that when we go through our examples. We'll be making this check. Lastly, we'll find a few points. We'll find x-intercepts and y-intercepts. Remember from quadratics and other functions, y-intercepts occur when you set x equal to 0 and calculate y. And for x-intercepts, we want values or places where y equals 0. So in a rational function, the only way that y can equal 0 is if the numerator of the function equals 0. Now we'll do this in the simplified version of the function because we don't want to find places that make both the numerator and denominator equal 0, because as we talked about earlier, those are called holes. So let's go through an example here. So our first step will be to factor our numerator and denominator. So we have a linear function on the top. Now on the bottom, we're going to want to first factor out a negative 2x using GCF factoring. And that's going to leave us x squared minus or plus 5x plus 6. And that factors into x plus 3 and x plus 2. And also we still have the GCF here. So now we have our original function in factored form. So let's go through and find these key elements. So our domain. So we start with all real numbers, and then we start excluding numbers. So we're going to exclude any values that make this undefined, meaning any values that make the original function equal to 0 in the denominator. So we're just solving the denominator equals 0. So we're using our zero product property and setting each factor equal to 0. So if I set that factor equal to 0, I get x equals 0. Here I get negative 3. And here I get negative 2. So we're going to put that as x cannot equal those numbers. So x can equal any number except for 0, negative 3, and negative 2. Now let's find our vertical asymptotes. I'm going to abbreviate that as VA for vertical asymptotes. So when we look for vertical asymptotes, we want to look at the version of the function after it's been simplified. So we know from simplifying rational functions, we can cancel our common factors. So after we've canceled, there's two values of x that make the function undefined. And that's where we'll have the vertical asymptote. So we have a vertical asymptote at x equals 0 and x equals negative 2. Places that make both the numerator and denominator equal 0, so that would be this x plus 3 before we canceled it out, that will be where there's going to be a hole. So when we draw our graph, we have to put a hole at x equals negative 3. Now let's look at our horizontal asymptotes. Remember, for the horizontal asymptote, we are comparing the degree of the numerator. In this case, the degree is 1 on the numerator, and our degree of the denominator was 3. So in this case, if we go back to our table, our degree of the numerator is less than the degree of the denominator. So it's this case here. So our horizontal asymptote is the line y equals 0. Now to look for our y-intercept, we would be setting x equals to 0, but we've already decided that 0 is not part of the domain. So in this case, there will be no y-intercept. The function's not defined at x equals 0. And to find our x-intercepts, those are at places that make, in the simplified version, make the numerator equal to 0. Well, we've canceled out our one value of x that would make the numerator equal to 0, negative 3, but that's not in the domain, so this one also does not have any x-intercepts. So if we add these features to our graph, we'll put dashed lines for our asymptotes. So at x equals 0, we've got a vertical line here. I put a little extra one here by accident, so let's get rid of that. And we have a vertical line at -2. And our horizontal asymptote is y equals 0, so the x-axis. And at this point, we don't have any other points to fill out. So at this point, we're going to bring a graphing calculator. Now remember, on graphing calculators, we will press the y equals button and type our function into y equals. Now, I've already entered our original function in here. Now you need to remember to put the parentheses around the numerator and around the denominator, otherwise it's not going to graph. So let's press zoom 6 to see what this graph looks like. Zoom 6 gives us a standard window. Now I've expanded this out, so if we want it to match, let's go ahead and change our window here to go from -5 to 5 on the x-axis and same on the y-axis. So we can see that over here we've got a hyperbola shape. Over here we've got a U shape, and here a hyperbola shape. And maybe we want to see how low this goes, so we can bring up the table of values. That's in blue here, second table. And let's get a value of x at -1. So at -1 we're at 0.5. So we can put a point here. That'll be the bottom of our U. And so we can let me try to sketch in here if I can a U. It's a little hard with this tablet. I'll do the best we can. So that should be not wiggly like that. It's going to be heading up and keep getting closer and closer to that vertical line, but not touching it. And if we go over here left of -2, see at -3 here, that's the hole we have. At -4, we're pretty close to 0, so it goes pretty tight here. So at -3, we're going to put a hole. We don't know exactly what that value is, but it's somewhere in there. So that's what our hole looks like. It just looks like an open circle here. And over on our right side here, we're just going to nestle right in here. Again, it goes pretty tight. If we wanted to get it exactly right, we could use that table to fill in. But we've got a pretty good graph here, and we see the key elements of where the function's not defined. And we see the key element of the hole. And as you can tell, you can't really see that hole in here. We went in the table, we saw there was an error at -3, but you don't really see it on the graph. You can kind of visualize that there are vertical asymptotes there. All right, so let's look at another example. So this is our second example. So let's start out by factoring here. So we want to factor out a 4x on the numerator, and we're left with x squared minus x minus 6. And the denominator, we can factor out an x using GCF factoring. And now we need to factor each of those quadratics. So on the top, we've got our GCF. And now we've got x minus 3 times x plus 2. And in the denominator, we've got x times, let's say here, x plus 4 and x minus 1. So now if we look at our domain, remember we are starting with all real numbers. And then we are excluding or accepting values of x that make the denominator equal to 0. So 0, -4, and 1. At those values, we're either going to have vertical asymptotes or holes. So values of x that only make the denominator equal 0 and not the top, so meaning not places where there's a common factor, that's where our vertical asymptotes will be. So we're going to have a vertical asymptote at x equals -4 and at x equals +1. And since the x is on both the top and the bottom. If we simplified it, it would cancel out. We're going to have a hole at x equals 0. So since the function is undefined at x equals 0, that's the value of x we would plug in to find our y-intercept. There's no y-intercepts. And when we're finding x-intercepts, we're looking at places that make the numerator equal to 0 after it's been simplified. So we want to throw out this version of x here because that's where there's a hole. So remember, to find numerator equal to 0, we're setting that entire numerator equal to 0. So using the zero product property, we would set each factor equal to 0. Here there's no solution. Here we get x equals 3, and here we get x equals -2. So our x-intercepts are at 3, 0 and at -2, 0. So let's put this information that we found algebraically on the graph. Let's draw our vertical asymptotes here at -4 and at +1. And let's put our horizontal asymptote here at y equals 4. Oh, I skipped the horizontal asymptote, so let's go back and fill that in. So the horizontal asymptote, okay, in this case, our degree is the same on top and bottom. So remember, when it's the same in that chart we had earlier, we look at the ratio of our leading coefficients. So our horizontal asymptote is going to be y equals 4. So let's put that on the graph. Let's go up 4. And we don't have any y-intercepts to plot, but we have 2 x-intercepts to plot. So we're going to be crossing the x-axis here. And we'll be crossing the, oops, that's in the wrong place, at -2 here. And at +3, 1, 2, 3. So I'm going to pause the tutorial here and bring on the graphing calculator, and I'm going to go ahead and enter that function. You don't need to watch me do that. All right, I'm back. You can see I've entered my function. Again, remember, we have to put the numerator and denominator. We have to put parentheses around the numerator and denominator when we're putting these in the graphing calculator. Otherwise, you're not going to get the correct graph. So to see the graph, let's press zoom 6. That'll reset my window. So we can see over here, we're curved up here. We've got like a S shape coming through here. And we've got a branch of a hyperbola over here. We could get some additional points, so let's bring up the table. So let me scroll over here. So at -10 here, we're at 6.3. So that's 5, 6.3, so we're about here. And at -6, which is here, we're up a little bit above 10. So we can use that to sketch this branch in over here. This would go up and be asymptote here, and this would keep going down and flatten out at x equals 4. So now let's look in this interval between the two asymptotes. So at -3, we're down here at -6. And at -2, we're at 0. We knew that. And at -1, we're up at 2 2/3. So we've kind of got this sort of S shape coming through here and down. It's hard to draw with this pen I'm doing. You get the idea. We saw the graph. And then if we go over to the right, we've got our x-intercept, and if we go maybe at 2, +2, we're down here at -2 2/3. So we know coming down this way, we're approaching that asymptote, and as we go out this way, we're approaching that asymptote. So that's our graph, and again, you can look at our graphing calculator, but we know additional information by doing the work we did. We know about these vertical asymptotes. We know the specifics of our x-intercepts. And in this case, we had a hole at x equals 0, so I guess I missed that. So let's go back and make sure we put our hole at x equals 0. So my graph is not correct. At x equals 0, there's a hole there. So right around here, we've got a little hole. So if we did this on a quiz or something, it wouldn't quite be right. So somewhere in here, there's a hole. So again, we don't really see that on here, but we know by the work we did over here about that hole. So I hope this works. It's as you can see, this video is long, it's time consuming, but we can get some good insight into the functions. Good luck with your attempts for doing these.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you